consider set W. In part A, we want to find matrix A such that the column space of matrix A is equal to set W. In part B, we are asked to find the if the column space of A is a subspace of Rk, what is K? And part C, we have that if the null space of A is a subspace of Rk, what is K? So, first things first, we gotta find matrix A. So part A, find A. So we need to take this set W and rewrite it as a linear combination of the column vectors. And we are given here set W defined as B minus C. We then have 2B plus C plus D. We then have 5C minus 4D. And last but not least, we have D. So if you can see it from here, by all means, go for it. Otherwise, you can fill in zeros for the missing places, and then we can rewrite this as a linear combination of the column vectors. So our first column here being related to the weight B. So I have B multiplied by the column vector 1, 2, 0, 0. Our next column vector is related to C, or weight C, so I have plus C multiplied by the column vector negative 1, 1, 5, 0. And last but not least, we have a column vector here for D, for our weight D. So this is plus D multiplied by that column vector 0, 1, negative 4, 1. Need a little more room. And so we can see our matrix equation here. We have matrix A 4x3 matrix, 1, 2, 0, 0, minus 1, 1, 5, 0, and then 0, 1, negative 4, 1, multiplied by vector B, C, D. And so we have rewritten this as a matrix equation. And so therefore, matrix A defined by column vectors A sub 1, A sub 2, A sub 3 is again that 4x3 matrix 1, 2, 0, 0, minus 1, 1, 5, 0, 0, 1, negative 4, 1. And this is our beautiful final answer here to part A. So we are ready now, keeping this matrix A in mind, to look at part B. And part B asks us if the column space of A is a subspace of Rk. What is K? So if the column space of A is a subspace of Rk, what is K? So we want to keep the theorem for the column space of A in mind here. So let's recall that if matrix A is an M by N matrix, then the column space of A is a subspace of Rm. So if A is an M by N matrix, then the column space of A is a subspace of Rm. So in other words, since the columns of matrix A, or since the columns of the M by N matrix A, each have M entries, the column space of A is a subspace of Rk when K is equal to M. So since the columns of an M by N matrix A each have M entries, then the column space is a subspace of Rk when K is equal to M. So for this example, we can say since A is a 4x3 matrix, each column of A has 4 entries. Which tells us that the column space of matrix A is a subspace of Rk when K is 4. So since A is a 4x3 matrix, each column of A has 4 entries, which allows us to conclude that the column space of A is a subspace of R to the K when K is 4. And last but not least, we have part C. And in part C here, we are asked that if the null space of matrix A is a subspace of Rk, what is K? And so just like we did in part B, to answer this question, we want to recall the theorem related to the null space of matrix A. So we have, if A is an m by n matrix, then the null space of matrix A is a subspace of Rn. So in other words, we can say that since the vector x that defines the matrix equation, matrix A times vector x, has n entries per the vector, then the null space of A is a subspace of Rk when K is equal to n. So since a vector x that defines the matrix equation has n entries, the null space is a subspace of Rk when K is n. So therefore, for this example, we can say since vector x here that defines this matrix A times vector x has 3 entries, the null space of matrix A is a subspace of Rk when K is n. And so this is our beautiful final answer to part C. So since vector x has 3 entries, the null space is a subspace of Rk when K, shame on me, when K is 3. And that is the real final answer.